Hi everyone, this is video 8 and today I'll be talking about environments for higher order functions. Today's video is going to be much shorter than the others because I want to mainly focus on this topic before I get into a completely different topic in the next video. So let's start with the example. This is a higher order function we defined in the last video, and I'm just going to go through the environment diagram for how this works, and I'm going to make a couple of observations and see how it's different from the environment diagrams we've worked with before. So what's the first thing we're going to do? We're going to define the make adder in the global frame as always, and then we're going to have a call expression. What do we do when we have a call expression? We define a new frame, then we bind the formal parameter n with the argument passed in 4, so that's done here, and then what do? We execute the body of the function. Well, the body of this function is different because we have another def statement, but that's easy enough. We just make adder a function bounded to the function adder k in memory. And then what do? Of course, we don't execute this because we don't do this until we call adder. And then, so what we end up doing is we return adder. So then the return value is pointing to a function, and then where does this return to? It returns to right here, and then that gets bound to add4. So add4 is now the adder function in the global frame. So now we're going to call add4 on 3. Well, this is the call expression. What is add4 really? It's adder. So now we make a new frame that has adder. And we also have this parent thingy. I'll talk about exactly what that is soon. And then, as always, we bind the formal parameter k with the argument passed in, which is 3. So now k is bound to 3. And then we return n plus k. What is n? N is 4, and k is 3. So I'll talk about the lookup procedure for this as well. But for now, we just know this is 7. So this is the environment for diagram for this function, and a couple interesting things about this environment. It's the first environment we've seen that's not only made up of a global frame and a local frame or global frame only. So here we now have an environment that's a sequence of 3 frames, one being the adder, one being frame 1, and the other being the global frame. So those are 3 frames, and that together makes up one environment. So let's talk about the execution rules for calling user-defined functions now. You might have noticed that there is this parent thingy. So why is adder's parent frame 1? Well, the definition of a parent frame is the frame in which the function was defined. So let's talk about how that changes the execution rules for calling user-defined functions. Well, as always, we first create a local frame, forming a new environment. And then, now what we do is we identify the parent of that function and copy it onto the local frame. And the parent function is, again, the frame in which the function is defined. So how does that work here? When we're calling adder, we have the intrinsic name adder, the intrinsic name being the name of the function in memory. And now, the second thing we do is we identify adder's parent frame. Well, where was adder defined? Adder was defined in frame 1, so our parent frame is frame 1. Now, intrinsically also, this make adder frame has a parent frame as well. But the parent, so let's ask what's the parent frame of make adder? Well, make adder was defined in the global frame. So the parent of frame 1 is just the global frame. But the reason the visualizer doesn't write it is because it's just a little too wordy. But in reality, the parent of this frame is also the global frame. So, and then once we add that little caveat, the rest of it is exactly the same as always. We bind the formal parameters of the function with the arguments passed in, and then we also execute the body of the function after all of that. But now this gives us a little different perspective on environments. What we've previously seen is either a global frame only, or a local frame followed by a global frame. This local frame followed by a global frame is shown here. And again, implicitly, I want you to, now that we know what parent frames are, the parent of this square frame is the global frame because the square was defined in the global frame. But now, there's a little different flavor to these environments. We now have seen an environment that's a sequence of frames starting from a local frame, followed by parent frames. There could be multiple parent frames, but in this case there's only one parent frame, and an ending at the global frame. So here we have an environment where we have this local frame adder. The parent of that is frame 1, and the parent of that implicitly is the global frame. So now our environment consists of 3 frames. Now, let's talk about looking up names in environments and how this changes with the addition of parent frames. The only thing different is we first look for the name in the local frame as always, but now if we can find it in the local frame, we look for the name in the parent frame, and we keep on doing this until we reach the global frame. So let's look at how this works. Well, so let's go back and look at this example. We define the make adder as always, so let's just go to the point where we call adder. So once we call adder, we return the body, return n plus k. So now this is where name lookup becomes important. We have to know what n is. Well, what's n? Let's think of our execution rules. We first look in the local frame, of course, and then we look in the parent frame, and then we look in the global frame. So let's look in the local frame first. Is n in the local frame? No. So where do we go next? We look at the parent frame. What's the parent frame? Frame 1. Where is n here? Yes, and n is 4. So now we know n is 4. Now let's look for k. What's k? Well, k we just find in the local frame immediately, and that's 3. So 4 plus 3 ends up being 7, and then we return 7. So that is how looking up names in environments change. The only change is that now we have to look, if we can't find it in the local frame, we have to follow the chain of parents until we reach the global frame. And if we don't find it after all of that, we know we have a name error in that the name wasn't defined. Now let's look at another example of composing a function. So this is another higher order function. And let's just go through how the environment for this works. We're going to define compose in the global frame. We're also going to define increment in the global frame. And now what we're going to do is we're going to call compose on increment and a lambda function. So this is also the first time we're going to see lambda functions in environments, and we'll talk about that a little more. So what's the first thing that happens? We create a new frame. We bind the formal parameters f and g to the arguments we pass in. What's the arguments we passed in? The increment function as f, and then the lambda function as g. Notice that the lambda function intrinsically has a name lambda, whereas the increment function has an intrinsic name of increment, and I'll get back to this point later. Now, what do? We go into the body of the function. What's the body of the function? We define h. So where is h defined? This is important. H is defined in frame 1, so remember this. And that's why they have parent is equal to frame 1, by the way, because we know that h is defined in frame 1. And now we return h. Awesome. So where does that get returned to? Well, that's returned to this giant expression. So now, what do we have? We have another call expression. We call h on 4. So the first thing we do is we create a new frame. Then we have to identify the parent of the frame. Where was h defined? H was defined in frame 1, so the parent of this frame is now frame 1. And then we bind the formal parameter x with the argument passed in, which is 4. So this is the only difference here is that we now have to figure out what the parent frame is. So that's just one little extra step. And then, of course, we execute the body of the function. So now we look for x. Well, x is in the local frame, so we call g on x. What happens when we call g on x? Well, g is intrinsically the lambda function. So now we have the lambda function with x bound to 4, and then what does it do? It returns x times x. So we execute the body of that function, get 16, and then now what do we do on that? Well, this entire thing is returned here, so now we call f of 16. What's f of 16? Well, f is actually the increment function. So now we have a new frame with increment as its name, and then we call it on 16. And then what do? We increment it by 1, as the function definition says, and we get 17. And where is that returned to? Well, that's returned to this entire thing. And then, what's happened with that? We would bind it to result, and then we're done. So this is how this works. So again, this is a pretty complicated environment diagram. Feel free to go back over it. And then, now the last thing I want to talk about is the differences between lambda functions and def statements. So def statements are these def square 1 of x, that's a def statement, we've seen them all over the place. And a lambda function is using the lambda notation. So there are only two primary differences. Def statements give functions an intrinsic name, And also, we can't have statements within lambda functions. So, to illustrate the intrinsic name idea, let's look at this example. So, when we define square 1 of x, what we get is we bind the name of the function, which is square 1, to the function in memory. And what's the name of the function in memory? Square 1 of x. So whatever the name is in memory, that is the intrinsic name of the function. So the intrinsic name of this function is square 1. Now, notice that this square 2 function is going to be the exact same thing basically as the square 1, but now notice that the intrinsic name of this function is the lambda function. So the only difference here that you see is that when you define a function with a def statement, you implicitly give it an intrinsic name of whatever you named it, whereas the lambda function doesn't do that. So when we call square 1 on x, we have the name of the frame being square 1, and then we execute it as always. But when we call square 2 on x, we have the name of the frame being lambda, because the intrinsic name of the function is lambda. The names of the frames are always going to be the intrinsic names of the functions that we call. So that's the only difference between lambda functions and def statements, and the only other difference that's really small is that you can't have statements within lambda functions. For example, it's impossible to execute a while loop inside a lambda function, or as far as I know, that's true. One thing you can do, but very annoying and I highly discourage, you can do if and else statements in lambda functions, but the syntax is really weird. I've only ever used it once, and it's honestly not really useful. Just use a normal def statement to do any if-else clauses. So, that's all I have for today. Again, this was a pretty short video. Next time, I'm going to go over in my opinion, one of the most important topics in computer science. So get excited about that. It's called recursion. I'll see you next time. Thanks.